Compound interest, part 4, the grand finale. Equivalent payments. For promissory notes in part 3, we did a little bit of mixing future value and present value in the same question. And now we're going to kick it up, big league style, with equivalent payments. You saw equivalent payments in Unit 5. You fell in love with it. And now we get to do it in the compound interest arena, the octagon. Okay, so the amounts of money, just to recall from our previous experience with equivalent payments, amounts of money, different periods of time, they're different, right? We got to look at things at a common time point. And we've seen this happen a few times already, right? We got to compare all the payments, the cash inflows, the cash outflows at a common date. Okay. So that's important. Selection of the focal date. Technically, mathematically, doesn't matter what you pick as the focal date. Just have to be consistent across all inflows and outflows. But there are easier focal dates and harder focal dates to pick. And we've had some experience with that, and we've seen that in a couple of problems already. Okay, so we know the focal dates are important, and we know that although it doesn't matter which focal date we pick, there are easier ones and there are harder ones. Okay, so I like to draw the timeline out, as you well know if you've watched any of these video clips. The timeline is extremely important. I find it very useful. I find it simplifies things, minimizes the amount of brain sweat I have to expend. But sometimes maybe you need some sort of rules of thumb to give you some guidance. And so we have a couple of rules of thumb here. One of the rules of thumb is if the due date of the payment falls before the focal date, use the future value formula, because that means the payment happens at a period of time and then we look forward to the focal date. Ooh, hey, look over there in the future, it's the focal date. And so we find the future value. And then conversely, if the due date of the payment falls after the focal date, we go, oh, we got to look in the back. Oh, look back there. There's the focal date. It's in the past. Let's go and let's find the present value. Yeah. So, there's those rules of thumb if drawing out the diagram and drawing out the timeline doesn't work for you. Okay. Other than that, there's no new material here. We're using the same two formulas. And basically they're really one formula, but we're using the same formulas as we've used all the way through chapter 9. Unit 9, two formulas. That's it. And we've just used it in so many ways. We've really sort of leveraged the value of these formulas and used them in a whole host of financial contexts. So we're just going to run through this example and just to see what's going on, and then we'll work out an example in a sec, okay? So we have debt payments of $500 due 3 months ago. Oops, must have missed that one. $1,000 today, $2,000 in 15 months, and are can be combined in one payment due 6 months from today. Okay, compounded monthly. Find the size of that payment. Okay. So we want to find the size of that one payment that'll take care of this entire loan with those 3 payments happening at those different points of time. So first step, after we draw this all out, and you kind of see the timeline on the slides, we have to now pick a focal date. The focal date is now the very important thing. And since we're trying to determine the equivalent payment 6 months today, that's going to get like the variable X, or whatever you want to call it. That is a very useful, very logical pick for the focal date. Again, mathematically, it doesn't matter what you pick as the focal date as long as you're consistent, but the easiest one is just to pick the time in which this one single payment occurs. Okay, so with that, we now look and say, okay, hey, the $500 due 3 months ago. Ooh, okay, so that due date was at one point in time, and then the focal date is in the future relative to that. So we find the future value of that $500. Right? Notice how many, because this one is compounded monthly. How many months from 3 months ago to 6 months from now? Right? That's 9 months in length. And so we find the future value. We've done that lots of times, and there's no controversy there. Okay. Second, we look at the next payment, $1,000, which is due today, but we're not going to really make that payment until we make this one big payment 6 months from now. And so we have to find the future value of that $1,000 because the due date happens before the focal date. Okay, so we find the future value and we sort of go into the future and we find the future value there. And then again, not very controversial. And we've done many calculations like that. And then we look and we say, hey, that $2,000, well, that's due 15 months from now, but we got to, bring it back to the focal date of 6 months from today. And so we're going back in time, right? And so we find the present value for that one. We add all these up, right? And then we add them up. We get the value of the payment, right? So when we split it up into little bite sizes, they're just a little series of little future value, little present value calculations. Nothing terribly complicated. We're just bundling them up a little bit, and sometimes in all that integration, not in the calculus sense, but when we're using a lot of concepts in the same question, things can appear to be or feel complicated. They're not. We just look at the little step by step, nibble by nibble. It's the same kind of thinking we had when we did linear programming. Right? Just, hey, take it little bit by little bit, nibble by nibble, and assemble it. All right. And so at the end of all this, the single payment that will cover all these three payments will be $3,437.04. Okay, so try that. You know what the answer is. You know what the logic flow is on this one. Give that one a shot and see if you could replicate that. That's always a great practice where you know the step by step, but you want to practice it so then you can then compare and see, okay, if you don't get $3,437.04, you can then maybe compare your methodology with my methodology and see where the gap is. So that's a great source of practice there. Okay, a couple of more scenarios. Nothing really new. We did it for one equivalent payment. We'll also can do it for two or more. 2, 3, 4. We'll just worry about more 2s and 3s. Equivalent payments. Okay, so you have a couple of payments, and typically what will happen is the 2 payments will be equal to each other, or the 3 payments will be equal to each other. Okay, we'll pick a focal date like we always pick a focal date. Now, because it kind of jumped out at us that when we had a single equivalent payment, that would be whenever that single equivalent payment happened, that became our focal date. It made sense. Now, doesn't really matter. We're going to have to deal with a nasty coefficient in front of one of the unknown equivalent payments anyway. So typically in these kinds of cases, I just pick today as being the focal date. The current period as being the focal date. Again, like I've said, and I'm probably getting tired of hearing me say this, mathematically, doesn't matter which one you pick as the focal date. As long as you're consistent, everything is fine. We'll pick today in these more complicated situations, usually today is probably the best in these more complicated situations, and that way I'm just comparing things to the current period. I don't have to do too terrible. I minimize making a little silly mistake in the counting of periods. That's all I'm trying to do here. Okay. All right. Okay. So let's see an example, and then we'll do some practice work. So Joe is due to make a payment of $2,500 now. Instead, he's negotiated to make 2 equal payments 1 year and 2 years from now. Determine the size of the equal payments if money is worth 7.5% compounded quarterly. Okay. Again, focal date is arbitrary. You can pick any one you like, as long as you're consistent. I'm going to pick today as the focal date just because it's nice and it's easy to work with. So what does this look like? We draw out our timeline, and we got something that looks like this, right? We got $2,500 today. We're replacing it with a couple of payments in 1 and 2 years from now. These are unknown payments. Call them X if you like. And so we find the present value of those x's, right? Because the due date of those two payments happen in the future relative to the focal date. Right? So we're finding a couple present values. Now, we don't know what that future payment is, right? So it gets represented as an x because we don't know what it is. The number exists. It's just unknown to us. And we've dealt with this situation a lot where the number exists. It's just unknown to us. X is a number, right? X is a number any more than 4 is a number. They're both numbers. X, when we say x, we're just saying there's a number here. We're not sure what it is yet, but it's there. It exists. We're going to discover it, but it's going to happen, right? We're going to discover it, but we haven't discovered it yet. So we find the present value, and so we get this kind of this ugly looking coefficient in front of the x. That's okay. We do the same thing for 2 years, right? Noting we're just doing the present value calculations like we do the present value calculations all throughout Unit 9, all throughout how you would have seen it in your high school math. Nothing new here. The only new thing is there's this x. It's an unknown. It's got a coefficient. No big deal. We've seen x's we've seen unknowns with coefficients before. We saw that a lot in Unit 2. Nothing special here. Okay. So, but we're still going to gather up all our x's just like we always gathered up our unknowns, just like we always gathered up our x's, whether we were in Unit 2, whether we were in Unit 5, whether we were in Unit 4, wherever we were, we gathered up these x's. And we'll do the same thing here, right? We just add those x's and we get 1.790292 times by x. That equals $2,500, right? Divide both sides by 1.790292, right? To isolate x, just like we always do, right? And we get the payment, $1,396.42. So we're making 2 payments of that amount, okay? So all we've done is, what's great about equivalent payments is we're integrating entire blocks of the class. First of all, we're doing everything in Unit 9 comes into an equivalent payments. We're drawing a timeline, which is so terribly important. And then we're pulling some of those basic algebra skills that we sort of reviewed at the beginning of this course, and we're bringing that into this question as well. So this equivalent payments, it has everything. It's great that way. Okay, let's do some practice problems where we're got to do that. I have got to do the writing. Equivalent payment practice. Okay, so question 1. So we got a bunch of scheduled payments. $800 due 1 year ago, $1,000 due 6 months ago. So clearly this client is in arrears. To be replaced by a payment of $400 now, a second payment of $1,000 9 months from now, and a final payment 18 months from now. So what is the size of the final payment of interest? Is 10.8% compounded quarterly. Step 1. Let's get the timeline on this all set out. Okay, so this one's a little bit tricky because we've got a lot of payments happening on either side of today. So we have 0. So what happened? We have 12 months ago, right? $800 payment was missed. And then 6 months ago, there was a $1,000 payment missed. Okay. Now those are being replaced. So I'm just going to make sure I put that on a different line so I just keep track of everything. By a $400 payment today, a $1,000 payment 9 months from now, and 18 months from now, some unknown payment. We give it the wonderful name of X. Single X, and that leads us to kind of make our life a little easier, and we'll pick when that particular X happens as our focal point, 18 months from now. What does that mean? Well, it means we have to look at each one of these payments, both sides, in terms of month 18. As month 18 is the focal date. So lots of future values going to be happening here, right? Okay, well, that's not so bad. So it's an equivalent payment, so we know we're balancing one payment structure with the other payment structure. So on one side of the equal sign will be the original payment structure, and on the other side of the equal sign will be the new proposed payment structure. What does that mean? Well, it means that future value of the $800, right, 1 plus 0.108 divided by 4, because it's quarterly. And now I'm counting quarters. So from 12 months ago to 18 months from now, that's a total of 30 months. 30 months, 3 months per quarter. If you like, you use little chapter 3 ratio or unit 3 ratio stuff, and you get 10 quarters between those two dates. Okay. Add to that the $1,000 payment, and again, still finding the periodic interest rate, and that is 6 months ago to 18 months from now. That is 24 months. That's 2 years. There's 8 quarters in 2 years. That will all be equal to, because I'm just splitting it into lines because I'm going to run out of paper, and it can be long. $400 payment, right? The proposed payment structure. Now that is to happen today, but we're going to look at everything in terms of month $18, just so that we can figure out what that extra payment needs to be. And so I am just going to shortcut this a little bit here and divide the 0.108 divided by 4, just so I'm not taking up too much space and it's not so difficult to read. Now, from 0 to month 18, how many quarters is that? 6, right? 18 divided by 3 is 6. Plus $1,000 payment on month 9, 1.027, and 9 months difference there, so that's 3 quarters, and then plus X, right? X happens on the focal date, so there's nothing extra to do there. Okay, so as you can see, the key components to make this type of question a little bit more challenging is the fact that we have many payments happening. We draw out the timeline, we see which future values we need to calculate, if any, we see which present values we need to calculate, if any, and then we just bring it all together. Okay, so it's just a series of little things just brought together in one question. Anyway, so once we work this all out, we get 1,044 with lots of decimal spots, plus the future value of that $1,000 payment, $1,237, and again a bunch of decimal places. And that is balanced out or equal to the future value of the $400 payment, which is a little over $469. Plus the future value of that other $1,000 payment, that $1,000 payment in the proposed structure. And then plus X, which marks the spot. Okay. So now we just isolate the X, do the little bit of algebra that we saw in unit number 2, and ultimately we get X is equal to $729.24. Okay. Right. Subtract both sides by 469 and some change. Subtract both sides by 1,083 and some change. And once we've done all that, we get an equivalent payment of $729.24. Okay, so lots of excitement in that one. Let's give question number 2 a shot here. So question 2, we have a loan of $15,000 borrowed today, is to be repaid in 3 equal installments, due in 1 year, 3 years, and 5 years respectively. What is the size of the equal installments if money is worth 6.2% compounded monthly? So now we have 3 unknowns, but they're all the same size, so they're all going to be X. And now we get to use a little bit of algebra along again with finding some present values, and we get to have a little bit of fun here. So first step, let's just find that. Let's do that timeline here, so we know when things are happening. So we get $15,000. We borrow that sum of money. And then we make some payments in 1 year, 3 years, and 5 years. I'm just going to put that little bit different line of X, X, and X. Now, when we were discussing this before, we said, hey, again, focal date, you got to pick one. Doesn't matter which one, somewhat arbitrary. Pick one that's the easiest. I picked today because that way I don't have to do any funky math as comparing a year in the future with another year in the future. You make mistakes that way. So let's just pick today as the focal date. Okay. So at 0 is the focal date. Okay. So we look at that first X, find the present value of the first X, find the present value of the second X, find the present value of the third X, add them all up, and they should be the same as this $15,000. So what does that mean when I write an equation? It means this $15,000 is going to be the same as the first X multiplied by 1 plus, what's that interest rate? 0.062 divided by 12 because it's compounded monthly. How many months in the first payment? Well, that's 12. Minus 12. Don't forget the minus. Add to that the second payment, which is again X. And I'm going to just do the math inside the brackets here because it's just a little bit shorter to write. And I get 1.005167. How many months from 3 years from now to today? 36 months. Don't forget the minus because it's present value. Minus 36. And then not forgetting the last X times by 1.005167. And then it goes back 5 years, which is 60 months, so minus 60. Okay. Okay. Do not add up the 3 X's. Go 3X equals to $15,000. X equals to $5,000. Because you're ignoring interest in that case. And that kind of defeats the whole purpose of compound interest. Okay. So nevertheless, so we have our $15,000. And now we just find the value of those, the coefficients for each one of those X's. And so I do the little bit of math here. And I get 0.940029 times by the first X plus 0.83306661 times by the second X, and then 0.734018 times by the third X. Now, a couple of things that will show me whether I'm on the right track or not. First thing is I'm finding all present values, so I expect all those coefficients to be less than 1. If I get a coefficient greater than 1, that's indicative of I forgot the negative sign in the exponent. Okay, if you put a positive exponent, you're going to get a value greater than 1. Okay, so all 3 of my coefficients are less than 1. That's my first clue that things seem to be good. As I get further and further into the future, payments that happen further and further into the future have more interest in them relative to their principal. And so I would expect the coefficient in front of the payment made 5 years from now to be smaller than the coefficient in front of the payment made 3 years from now, and to be smaller than the coefficient made 1 year from now. And I see that my biggest coefficient is from the first year payment, my second biggest is from the third year payment, and my third biggest is from, or my smallest, is from my 5th year payment. That fits with what I would expect it to be if I had done the calculation correctly. So everything indicates that it's all good so far. So let's go and we get the 15,000, gather up all our X's, and we add all those X's together, all those coefficients. I get 2.504708X. Divide both sides by 2.504708. Yikes, what a mouthful. And I get $5,988.72. Okay. So you're going to make 3 payments of $5,988.72, and that'll take care of this loan of $15,000 at an interest rate of 6.2% compounded monthly. Okay. So lots of excitement and lots of fun in that one. Let's do one more payment. One more payment. One more question. All right. Question number 3. So we have a payment of $600 is due in 6 months. Interest is compounded quarterly at 4% in the first 6 months and compounded at 6% monthly thereafter. Okay, so we've got a couple of things going on here. These two payments are replaced by a single payment 9 months from now. Determine the size of the replacement payment 9 months from today if the focal date is 9 months from now. Okay, it has the markings of a very complicated problem. Anyway, so let's look. Let's draw out our timeline. So what do we have here? We have 6-0 being today. 6 months from now, there is a $500 payment that is due. And 9 months, what happens? Second payment is due in 18 months. Okay, so let's break out in 18 months. And that second payment is $800. And those are all to be replaced by a single payment 9 months from now. So 9 months from now, one single payment. Okay, so following our typical convention, we pick X to be the focal date. It minimizes the complication in more ways than maybe is immediately apparent. So if I look at the $500, and that goes to the future, to month 9, and the $800 goes to the past, to month 9. Or the $800 is in the future at 18 months, goes into the past at 9 months. I will find those two values, and they should be equal to the X. Now, what has happened? Interest is compounded quarterly at 4% in the first 6 months. I'm not doing any calculations in the first 6 months. I don't care. Right? It's already worked. It's already baked into the $500 payment. It doesn't matter to me. Whoa, cool, right? So here the focal date, not only do you not have the nasty coefficient in front of the X, you don't have to deal with the second interest rate. So if you made today the focal date, not only would you have a nasty looking coefficient in front of that X, you'd have to work out the two interest rates. You'd have two interest rates colliding together, right? Adding an extra level of complexity. All right. So now we've kept it simple, and we've picked a focal date so we can avoid that, the dueling interest rate problem here. So that X is now becomes pretty straightforward. Future value of the $500, 1 plus, what's the interest rate? 6%, 0.06. And that one's a monthly one, so divide by 12. How many months from month 6 to month 9? That's 3. It's positive because it's a future value. I add to that the $800 payment, which is 1 plus 0.06 divided by 12. We go into the past 9 months. It's a present value, so it's a minus 9. X then becomes equal to $507 and 0.537563, so lots of decimals, 563 plus 764, 883744. And ultimately, X becomes $1,272.42. And there we sit, right? So the complexity here is to pick a focal date. If you have two interest rates and you can avoid having to deal with both of them, it's not impossible to deal with. It just means you have another interest rate factor that you bring into each one of these payments. It just makes things longer. It doesn't make things any really harder. It's just more writing. But we'd like to minimize the number of writing and the amount of complexity. Okay, so we have that. And that is basically sums up equivalent payments. Okay, so Unit 9, two formulas highly related to each other. We have a future value formula. We have a present value formula. We use them in a variety of contexts, right? And as you can kind of see, just right now, lots of usefulness in those two formulas. And then we did a little bit of work with promissory notes. Key thing is, remember how we deal. The promissory notes essentially are done the same, except with interest bearing versus non-interest bearing, there's a couple of steps in one versus the other. Go look at and see which one is the mysterious one. Okay, so you want to refresh that. They both require a maturity value. You'll both discount that maturity value to the date of sale or the date of transaction. They're both the same that way. One already gives you the maturity value, and the other one doesn't. Ooh, now you want to go look and see which one does and which one doesn't, right? And then we brought everything together with the equivalent value payments. We did future value, we had present value in the same calculation, and that was kind of cool too. And that sums it all up for unit number 9. Thank you very much for listening.